Okay. Here we have two intersected beams. They are intersected at point E. There is a beam AB that has an uniform distributed load, and another simple beam CD that doesn't have any loads. Okay? They are intersected at point E. And again, it's required to do the shear force diagram and then the moment diagram. What is the structure system? What is the structure system? I have to understand the structure system so I can know what the condition will be. Okay? Here there are two intersected beams. So there is one above the other. There is one beam above the other, like this. But I don't know if the black one is above or under, or the red one is above or under. Okay? Why do I don't know which one is underneath the other one? Because both of them are simple beams, so both of them are stable. So what will be the closest example to this one? That I knew that there are one above the other, but I don't know which one is above the other, because both of them are stable. Both of them are stable. So this one is the same like the last example. Compound beam with two parts, stable parts. It's the same, it's copy-paste, the same idea. How did we solve this example? When we solved this, I didn't know which one is the main and which one is the secondary, so I put them on the same level like this. The only information I knew here, because there is a compound beam, there is one above the other, so I knew that there is a reaction here and another reaction on the opposite direction. This one, the last example we solved the last week, right? This would be the same exactly. How? I don't know which one is the main, which one is the secondary, because both of them are stable, the same meaning, right? But the only thing that I know that at point E, there will be two reactions that have the same value but in the opposite direction. So let's see how will we solve this. So here is the first beam, A, B, that has a uniform distributed load. And here is the second beam, and they are on the same level, C, D, that doesn't have any loads. This one, point E is in the middle, and this one, point E is in the middle too. The dimensions of A, B is 3 meters and 3 meters, and CD 4 and 4. What about point E? Here there is a reaction called R, and on the other side another R, but on the opposite direction. So it's the same idea as a compound beam with two stable parts, no main, no secondary. Both of them are on the same level. So let's calculate the degree of indeterminacy. It will be 1, 3, and the force will be R. 4 minus 3 is 1. And the main system, I will remove the R, and here the same, the main system, I will remove R. I will not solve it in the end, I'm just giving you the idea. because we already did the same one last week, okay? And also when drawing the shear force diagram and the bending moment diagram, I will draw for each beam individually, okay? What will be the condition? What will be the condition? The same. There are two intersecting beams, one above the other. When point E has a vertical deformation, a vertical displacement, these are structure systems that are connected to each other, right? So when point E of the red pen go down, will it go down individually by itself, or this is a connected structure? They will go with each other. They will go with each other, right? So the deformation delta E for the red pen will be the same delta E for the black pen. So here the condition will be at E. So delta E for AB the same equal to delta E for CD. The same condition like a compound beam with two stable parts, no main and no secondary. Okay? Let's solve this one. This is an advanced one. Also two intersecting beams. The first beam AB, a cantilever, and the second beam is CD, another cantilever. But on the intersection there is an extra spring. Okay? There's an extra spring. How will we deal with this example? First, without the spring, what was the degree? It was once. Here is 1 and here is 1, but they are the same one. Here is R and the other side is R. So the degree of this example was 1, degree of indeterminacy. So what will be the degree of indeterminacy if we added a spring on the intersection? So a spring has an extra reaction, only one reaction, right? So the degree of indeterminacy here will be 2. So this one will be twice statically indeterminate. Okay. What is the structure system? Let's think about the structure system here. Without the spring, and then when we added the spring. First, this is AB, the first cantilever, that has a uniform distributed load. I think the intensity is 2 nanometer. And the other part, another cantilever, CD, has only a vertical force at D. Take care, the intersecting point here is on the edge, B, but here the intersected point B is not on the edge. Just take care of that. So the span here is 4 meters, and here the span is 3 meters, 1 and 2. Okay? If there wasn't a spring, so what will be the reaction here? R and R. Here there was only 2 partners, right? AB and CD. So when we go for the 2 beams and get them intersected again, was there any load at point E? Was there any load called R on point E? No. The R, I saw the R because I dealt with each beam individually. When I return them to the original part, the R will go away with the opposite R, right? Here, how many partners do I have at point B? I have 3 partners. B for AB, and B for CD, and a spring at B. So I have 3 partners. So does it make sense to put here R and an opposite R on the other side? Doesn't make sense because there are 3 partners now and the spring has a reaction, right? So if this is R and this is an opposite R, so what will the spring reaction will be 0. It's not 0. It's a support that has to have a reaction. So here we will put R1 and the other side will be R2. And what will be the reaction of the spring? R1 plus R2 or R3, and R3 will be R1 plus R2. So when we turn this to the original structure, was there any R's at point B? No. So they have to be cancelled with each other, right? Here there was only 2 partners, so R upwards and R downwards, they were cancelled. Here I added an extra partner, a third partner. So each partner has to have his own reaction. So I will put here R1, R2, and I will convert them R1 plus R2 on this one. Okay? So let's solve this till the end. What will be the first step? I will start from part AB. What will be the first step? The degree. What will be the degree? 3 and 4 redundants minus 3 equations, so the degree is 1. What is the degree here? The same. 3 and 1, 4 minus 3 is 1. But is this one the same as this one? No, they are different. This is R1 and this is R2. But here, this one and this one are the same. That's why this was once statically indeterminate, but this is twice statically indeterminate because this one is different than the other one. Okay? So let's continue. So what will be the main system? The main system. So remove R1. So the redundant will be R1, and here the redundant will be R2. So the main system will be like this, a cantilever. This is the case node or the main system. Okay, let's calculate the reaction to draw the bending moment that it's called M node. Here 2 times 4 is 8. So this reaction will be 8, and what about the moment? It will be 8 times 2, which is 16. Let's double check the intensity of the distributed load. Is it true or not? The intensity is 1 time per meter. So here it's 1 times 4, and the reaction here is 4, and the bending moment will be 4 times 2, which is 8. Okay. Let's know the bending moment, M node. The moment at the edge here is 0, the moment at A is 8, and then PL square over 8. This will be the bending moment diagram, that's called M node. And we will put it on a conjugate beam. What will be the conjugate beam here? Fixed will be free, and the free will be fixed. What do I want to calculate? What did I remove? I remove a vertical force at point B, so I need to calculate a vertical displacement at point B. What is the definition of the vertical displacement at a point from the deflection? It is the bending moment or the moment at this point from the conjugate B. So now I need to know the moment at B. So I need to calculate the areas of the bending moment first. What's the area here? Let's calculate the PL square over 8 first. It's 4 square divided by 8, which is 2. So I have here, will we make any splitting? Again, I have 2 positions. I have to split the areas of the moment at. What is the first position? if there is a difference in the inertia, I don't have any difference in inertia here. And at the point that I removed a redundant at, or the same meaning, the point that I will calculate a displacement at. So I will calculate the displacement at B, so it's already split at B. So I don't need to split any extra splits here. So I have a triangle upwards, 1/3 and 2/3, and a parabola downwards in the middle. What is the area of the triangle? Half. Base is 4, height is 8, so it's 16. And here the area of the parabola is 2/3. Base is 4. Height, what is the height of the parabola? The height of the parabola is the PL²/8, so it's 2. Divided by inertia factor, which is 1 in the whole example here. How much will be? 5.33. Now I need to calculate delta at point B, which is called delta 1 node. Delta at point B, which is the moment at B. Let's calculate the moment here. I have two forces. The first force, 5.33, upwards, so negative 5.33, which is in the middle, so times 2, plus the 16 times 2/3 of the 4, which is, I think, 2.67. All of this divided by ER. So delta 1 node here will be equal to 32. Positive 32 over ER. This is delta 1 node. Let's continue to the other port, CD. The degree is 1, the main system I removed the R2, so the main system will be like this, only having 2 done at point D. But don't forget that you removed a reaction here. Just remind yourself that you removed the reaction here at B, so all the moments, all the area of the moments will be split here, okay? You didn't feel this on the other part. Why? Because the other part, the point that you removed the reaction at was on the edge. So you didn't feel that there is a problem, right? But here the point that you removed the reaction at is not on the edge. So take care. Let's calculate the reactions to draw the bending moment diagram. Only I have 2 tons, so the Y here will be 2, and the bending moment will be 2 times 3, 6, right? Let's do the bending moment diagram. Take care when drawing the bending moment diagram. Here the moment is 6. Here the moment at D is 0, right? And then straight line, knowing from distributed load, so straight line. Put it on the conjugate beam, so this is called M node, plus conjugate beam. The conjugate beam here fixed will be free, and the free will be fixed. Can I calculate the area of this triangle right away? No, I have to split it at point D. How can I know this value? I have 2 options to know this value from similarity of the triangles, or this is a bending moment diagram, so I can calculate the bending moment here. What is the bending moment here? It's 2 times 1, which is 2. Easy. Or for similarity of the triangles, it will be also 2. Okay, so here I have a triangle, and here I will be having a trapezium, which will I divide into a rectangle and a triangle. So the trapezium here is upwards, so the rectangle is in the middle, and the triangle 1/3 and 2/3. What do you think? Do I need to know the reactions at point D? What do I need to calculate? The same. I need to know the delta at point B, which is called here delta 1 node also, but delta 1 node dash or star just to differentiate between the two delta 1 nodes, okay? It's a moment at B here, right? So from the left-hand side, I have only two forces, right, from the free end. But for the right-hand side, I will have to calculate the reactions. So I have here the option not to calculate the reaction and waste the time, right? So let's calculate the moment at B from the left-hand side. I have only two forces. Let's calculate the first one. It's for the rectangle. So it's 2 times 2, 4. And here is for the triangle half. The base is 2. And the height is the difference between 6 and 2, which is 4. So it will be also 4. Okay. So let's calculate the moment here. Both forces have a positive sign. Both of them, the tail of the arrow will be down. So the first 4 of the rectangle, 4 times 1, positive. And the 4 other force, which is 4 of the triangle, 4 times 2/3 of the 2, which is 1.33, divided by EI. So it will be 6. I don't think so. 4 times 1.33 is 9.33, right? Yeah. 9.33 positive divided by EI. So delta 1 node is positive 32 divided EI, and delta 1 node dash to start is 9.33 divided by EI. Okay, what will be the next step? Case 1 for each part. Case 1 for each part. The first part, which is AB, this is the main system without any loads. I already took the loads in case no. This is case 1. And at point B, do I have the option to put the unit load of the R1 I removed on any side, on any direction? No, I chose the direction here. It's upwards and advise. Usually do this direction upwards and let the direction on the spring be downwards. Okay, this is the regular reaction for the spring to be downwards. So here I will put the unit load X. Let's name here X1 is R1 and here the X2 is R2. They are different. I can't call both of them X. So X1 is R1 and X2 is R2. So here X1 equal 1. And then I will draw the bending moment. The moment here is 1 times 4, which is 4. So the bending moment diagram will be 4 and 0. This is called M1. I will put it on a conjugate beam. Fixed will be free and free will be fixed. I don't need any splitting. What will I need to calculate here? The delta at point B. Delta at point B, what is it called now? Delta 1, 1. The moment here, I only have one area, one force. It's a triangle, half base times height, half 4 times 4, which is 8. I need to calculate the moment here, delta be the moment here. It will be 8, negative 8. The tail of the arrow is upside. 8 times 2/3 of the 4, which is 2.67, divided by EI. So delta 1 here will be 21? 21.50 divided by EI. Okay, what about the other part? CD, the main system. I will remove any loads. There was only one load at D. I will remove it. I will just put a unit load instead of the reaction I removed. So here X2 will be equal to 1. Here's B, and here is B, and here is C. Let's calculate the moment. So the moment here will be 1 times 2, 2. So let's calculate, or let's plot the M1 star. Let's put M node star, because this is M node, and this is M1, so this is M1 star. The moment here will be 2, and here the moment will be 0, and here the moment will be 0, so this will be the bending moment diagram. Let's put it on the conjugate beam. Fixed will be 3 and 3 will be fixed. The same I need to calculate here at B. So no need to know the reactions on the right hand side. I just need to know the area of the triangle which is on the left hand side. It's down the data, so it's downwards. Half base 2, height is 2, so it's 2. So let's calculate delta B, which will be called delta 1 star, moment at point B. Only one force, negative 2 times 2/3 of the 2, which is 1.33, divided by EI. So it will be equal to negative 2.67 divided by EI. What will be the condition? What will be the condition? When there were only 2 partners here, what was the condition? These are one structure, they can be split. So when the point of intersection moves downwards, so both of them will move downwards the same deformation. So the condition was that the deformation at E for the red pen, AB, will be equal to the deformation at the same point for the black pen, which was here C. Okay? Here there is a spring. So what will be the condition? Now there is a spring underneath. The spring has a vertical displacement. It's not a roller support, right? So it has a vertical displacement. So, and all of the structure system the same, they are connected to each other. So what will be the connection? So what will be the condition? If the spring move downwards, compressed, so all of them will be compressed the same. So the condition here will be delta condition at B. So delta B for AB will be equal to delta B for CD will be equal to delta B for the spring. Right? What's the delta B for AD? AB. So the delta at B, delta 1 node plus x1 delta 1 1. And the delta B for CD, it's from case node and case 1. So it will be equal to delta 1 node star plus x2 delta 1 1 star. And what will be the delta of the spring? We knew the equation for the spring last lecture. What was it? The force of the spring. The force of the spring equal to the stiffness multiplied by delta, right? So if I need the delta, it will be equal to the force divided by the stiffness. What is the force of the spring? The force of the spring is R1 plus R2, which is x1 plus x2, divided by the stiffness of the spring. He didn't give me the value of the stiffness of the spring. He just told me that it's EI divided by 5. So all the deltas here is divided by EI divided by EI divided by EI. And this is EI divided by 5. So the 5 will jump upwards, right? And now I can cancel all the EIs for the whole equation, for the 3 parts of the equation. So here when he gave me the value of EI, it was just a trick. I will not use it. Because on the other side he gave the stiffness of the spring in terms of EI. When will I use the value of EI? If he like give me the value of the spring stiffness, like 2000, 3000, whatever, he didn't give it to me in terms of EI. But here, he gave me the spring stiffness in terms of EI, so I don't need the value of EI, the 5000, I will not use it. How many redundancies this equation have? 2. X1 and X2. But these are 2 equations. This is not only one equation. I will use the first 2 parts, delta 1 naught plus X1 delta 1 1 equals delta 1 naught star plus X2 delta 1 1 star. So this will be the first equation in terms of X1 and X2. And then the second equation, take any of them, this or this, and take the third part equal to each other. So I will get another equation in terms of X1 and X2. Solve the 2 equations with each other, so I can here get X1 and X. And then when I draw the shear force at any moment, I will draw for each part individually. Okay, let's talk about something called yielding of support. What does yielding of support mean? Like, for any conditions, my structure or my structure supports have moved for any reason, for any condition. Here, he's telling me draw shear force diagram and bending moment diagram due to the shown loads, in addition to a vertical displacement at B equals 1 centimeter. For any conditions happen, the point B moved a vertical displacement of 1 centimeter. Okay. What will the movement that happened in this support will differ in my solution? It will differ in 2 parts. The first part, let's calculate the degree of indeterminacy. 3 and 1, 4 redundant, minus 3, so the degree of indeterminacy is 1. What about the main system? Let's remove 1 redundant. Here you don't have the option. Here you don't have the option. What if it's a regular example? So they can say I remove the roller support at B. So the main system will be fixed free. And then Abdullah will say, no, I remove the hinged, I remove the moment at the fixed support, so the main system will be hinged roller, simply. When there is a yielding of any support, you don't have the option of choosing the main system. You have to remove the reaction that is corresponding to the displacement that happened. Here he's telling me there is a vertical displacement that took place at B, so the main system I have to remove the vertical support at B. So the main system here will be fixed free. I don't have the option to choose. Okay? What if he told me, draw shear force diagram and bending moment diagram due to the shown loads, in addition to a rotation at A equals 0.00. quickly. So there is a rotation that took place at point A. So the main system will be hinged roller. I have to remove the reaction that is corresponding to the rotation that happened. So here will be the main system for the vertical displacement. If you told me in addition to a clockwise rotation at A equals to 0.001 radian, what will be the main system? Will be hinged roller. This will be the main system here. So I have to remove the M. Okay. What will be the condition here? And what will be the condition there? The condition here, condition at B. If there wasn't any displacement that happened, any yielding support, so B is a roller support, so it can't move vertically, so delta B equal 0. But here he told me that there is a vertical displacement at B. So the condition delta B will not equal to 0, it will be equal to 0.01. This is the 1 centimeter. I converted it to 0.01 meter, not 0. And in this case, I have to give you the value of EI, because it will not be cancelled, because the right hand side will not be equal to 0. Okay? What about the sine rule? For the rotation, the sine rule will be the clockwise rotation. The clockwise is positive. If it's anti-clockwise, it's negative. What about the vertical displacement? The sign of the vertical displacement, if it's downwards, this is the positive. Downwards is positive. So downwards, positive. Upwards is negative. Because the normal deflection is down. This is the normal one. So that's why we give it the positive. It's not normal for the point to move upwards, so we give it the negative side. So here he didn't tell me what is the direction of the vertical displacement, right? He just told me a vertical displacement. So I have two options here. Either he will tell me or a downward vertical displacement, a downward vertical displacement. So downward, so it's positive. So here in the condition, it will be positive 0.01. Or he will tell me there is a deflection at B equals 1. So the deflection means it will be downwards, without telling you a vertical or a downward vertical displacement. So either he will tell me a downward vertical displacement or an upward vertical displacement, or if it's only like a deflection, it will be automatic. Downwards, it will be positive. So here the condition will be delta 1 known plus x times delta 1 equals 0.01. So I have to know the value of EI, and here the condition will be delta 1 known plus x times delta 1 equals positive because it's clockwise 0.001, and I have to know the value of EI.